I'm assuming that most people who click on this video won't have any idea what the title is talking about. If you do, fair enough. What a nonogram is something I'll get into later. What a state space is, well, that's the amount of ways you can organize something. For a 10 by 10 nonogram, that answer is 1,267 octillion,
Oh my God!
650 septillion, 600 sextillion, 228 quintillion, 229 quadrillion, 401 trillion, 496 billion, 703,205,376. So now that you know that very useful information, let's go on to learning what a nonogram is. Take it away, Jimmy. So, here is a very basic nonogram. And how it works is you are given numbers on the left and above, and you are supposed to fill in the grid according to the numbers. So, when we're given a 3 on the right here, that's telling us that in this row, if we would go along this way, 3 of these cubes would be highlighted. When we see a 4 here, that's telling us that if we go down the column like this, 4 of these cubes should be highlighted. Then, when we see something like this, where you've got a 1, then a 2, what that's telling you is that along this row here, you're going to have 1 cube filled in somewhere, then a space, and then 2 cubes filled in somewhere. So you can't have 2, then 1, or have 1 and then 2 directly next to it. There has to be a space between. Because if you think about it, if you've got 1, then a 2 here, that would make a 3. So put a 3 here instead. And that's all the logic that you need. And so off the bat, with this one like this, you can use a little bit of intuition. We know this is 1, 2, 3, 4, 5, a 5 space column, and 4 of these are filled. If we think about it, 4 can only fit in this column by going 1, 2, 3, 4, or by going 1, 2, 3, 4. So we know that 1, 2, 3 must be filled because the last one will either be here or here. The same can go for the next column over. We can now look at some other rows or columns, but we're looking at the rows because I've seen something. These 2's here, they've now been satisfied. So what we can do is we can ignore these squares. I think, yep. You can generally get us crosses to show that those squares aren't usable. Another piece of logic we can use, we know this column is a 2, so that means it cannot possibly go here because you can't fit two blocks like that. So we can put across there. That leaves 2 block spaces. Boom, boom, done. Look at this row. 1, then a 2. We know that that row's done. We go down here. This is a 3. We can see that a 3 can only fit here, so that's that row done. We can see that both the 4's are now done. We can do that. We can now see that there's only 1 space for that 1 there, and then we could put the 3 there. And there we go. And that is how nonograms work. If we were to solve a new one, let's just do it really fast like this, so I can flex on the haters. What are we working with there? There we go. 3, 4, 3. We go there. Here we go. There we go. Boom, boom, bing, bam, and there you go.
I like it, Kudgy.
Well, now that you know what a nonogram is, we're now going to delve into the state space search. State search of the seashell on the space search of seashores. So, where we start is Python.
No.
Ah, pranked. I don't have any Python code to show you. It fucking came out shit in recording, so I'm going to use some infographics. That means I get to test out editing a little bit more, don't I? Ooh, just lovely. Just, splendid. In the background you'll also notice I'm doing a 40 by 40 nonogram, which I found on a Japanese website. So that should be fun as a kind of backdrop. Anyway, let me begin with the explanation. So as my assistant has so kindly faded this 3x3 grid onto the screen, what we are going to explore here is how many different configurations we can make of nonograms using a 3x3 square. It's a very basic example and it's a good way to get some visualization in on what we're trying to do. So first we got to imagine all of the possible states that a nonogram could take on this 3x3 grid. The first states we shall be considering are when there are no squares on the grid. So when there's no squares on the grid, how many ways can you arrange that? Well, we've got it right in front of us, only one. That's the empty grid, and that will be one configuration. The next one we can try is when we have a one square lit up. Now, how many different ways can we configure one square being lit up on this 3x3 grid? Yes, that is right. 9. Correct. Well done. Very nice, very nice. So, now we're going to move on to the harder stuff. How many configurations can we have when there are two squares lit up? Now, this might take a little while, so feel free to pause the video here and calculate if you want to. I'm going to say the answer now, so if you haven't paused the workout, your fault, not mine. And the answer is 36. If you got it at home, ladies and gentlemen, congratulations, you've done a good job. I'm very proud of you, actually. So, I'll do a quick rundown of why that is the case, using some visual examples, which I'll demonstrate with our lovely graph above. So, the way I first looked at it was, we take these two smiley faces here, or two lit up squares, and we just move the second one around the same way we did when there was only one lit up square. And by doing that, we'll end up with 8 different configurations. And now what we must do is move the first one. So we'll move the first one to the second spot, and we'll move the second one to the third spot. And now we'll do the exact same again, moving the second one around the same way that we did with the first when there was only one square lit up, and we'll end up with 7 configurations. The reason why we've ended up with one less is because, for example, if I was to move the second one to the first cube, that is already a configuration we have discovered, and in fact the configuration which this diagram has been left resting in for a little while. If we then follow this pattern, we'll then find that the next one down, when we move them across, we'll have 5 configurations, then 4, then 3, then 2, then 1. So we end up with a sum of 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1, which gives us a grand total of 36. Now, we have to imagine when there are 3 squares lit up on this grid. You can pause the video to calculate yourself. Meanwhile, on the screen you will see the infographic run through all the configurations. I don't really have much to say over it because I feel like I animated the whole thing. I'm just going to show it. Okay, I'm very tired right now because it took me a little while. So here, I'll just throw in some random music. Enjoy yourself. Oh shit, okay, let's get on with it, I guess. So, the grand total of the amount of combinations you can have is 84. Yes! Maybe you counted that, maybe you calculated, yes, maybe you saw it coming, maybe you paused. I don't know. If you got that number, well done, that's pretty good. The infographic showed why this is the case. If you do watch it again, you'll see that it is 84. But to give a brief explanation of what's going on here, we have to imagine the previous two cases and how they worked. I will put numbers on the screen to help illustrate my point. But first, just imagine it as if there was 2, and you just can't use the first top left cube. That means you would have 7 configurations, then 6, then 5, then 4, then 3, then 2, then 1. And that would give you the first set. And that is the same way that we got a set from having only 2. Then we have to move the first filled up cube to the middle of the top row. We then do the second configuration again, and we'll end up with 6 plus 5 plus 4 plus 3 plus 2 plus 1. We would then go on to the next configuration or set, which is 5 plus 4 plus 3 plus 2 plus 1. We then go on to 4 plus 3 plus 2 plus 1, then 3 plus 2 plus 1, then 2 plus 1, and then finally just plus 1. If this rather brief explanation done by me is rather shit, then I would recommend going back and watching the infographic I made earlier. I would have tried to copy and paste it underneath the numbers, but it looked awful. So just go back and count along with the different sets. So you saw how the numbers appeared in the rows. See if you can see that first row, and then see if you can see the second row, then the third row, then the fourth row, and yada yada. And hopefully you'll get it down in your head how 3 squares configurations work. Now we can move on to the lovely headache of 4 square configurations. I'm not going to do an animation for this one, and I won't put any equations up. I'm just going to tell you that the answer is 126. The way that you get to this is following the same logic that you did to extrapolate 2 square configurations to 3 square configurations. You just got to add another loop in, because you now have that extra square. If any of that makes sense to you, I'm glad that you understand me, because I probably make no sense to anyone right now. However, you'll see there's a much easier way to imagine this as we get further on into the video. So, for 4 square configurations, 126. Now we get to an interesting maths shortcut. So, we're on 5 square configurations. What can you see? Well, there are 5 filled squares and 4 empty squares. Let's reverse the logic. Let's now try and find all the configurations for 4 empty squares. Hold on. We've already done all the configurations for 4 filled squares. So what does that mean? Well, quite simply, we can just double the number that we got for 4 square configurations and make that the 4 configurations plus the 5 configurations. So if we were to then follow this same logic, we could then say the same for when there's 6 filled squared configurations, we just double the number that we got for the 3 square configurations. If we have a 7 square configurations, we just double the number we got for the 2 square configurations, and so on and so forth. And we end up with the number
512.
So, we've run through all the ways that you can gather all the configurations for a 3x3 grid of a nonogram puzzle. So, now let's have a look at 4x4 nonogram puzzles. And let me tell you, the numbers definitely get quite large. And because they're so large, I'm not going to show you all of the method that goes into it. I'm just going to tell you the final answer. You want to know what that number is? You want to know the difference in size? Okay, here it is. It's 65,536 different configurations. How do we get to that number? We use Python. I am not going to hand calculate that for shit. Come on now. Fuck off. Who do you think I am? I was going to say Steve Jobs, but he didn't do maths. He did computer science. Whatever. Anyway. One small point that I just wanted to make is that when you're working with a 4x4 grid or a 6x6 grid, a even by even grid, the amount of terms you double changes. You can't double every single one up to a point. There is a middle point which you only do once, you do not double. For example, I'll put an infographic on the screen. In a 4x4 case, if you have 8 squares filled up and 8 blank, you do not double this value, because there's only ever one way of doing this configuration. If you follow the logic, you'll come to this conclusion. Otherwise, when you have 7 filled squares, you can double it because that's the same as 9 filled squares, and so on and so forth. So, now that we have a consistent way of looking at the search spaces for nonogram puzzles, now that we have code, or I have the code, you don't. Actually, I can provide the... Fuck it, I'll provide the code. Look in the description. I'll provide code. It's shit, but use it. Anyway, now that we all have the code, we can explore any set of dimensions. However, I did mention earlier there will be an easier way to look at this, and this is where things start to get interesting, and why I love math so much. To see what we're about to talk about, let's go back to the 3x3 grid example. So, after our very long, just time-consuming effort of finding the configurations through manually looking at them, we got a total of
512.
So the interesting thing to note about the number
512
is that it's even. What can you do with even numbers? Divide it by 2. So, let's go ahead. We'll divide it by 2, and we get 256. And to all you computer science nerds out there, this number may seem a bit familiar because this number regularly comes up in lots of bit encryption. So you've got 256-bit encryption. When you've got 8 bits, you can get 1 off this number. Blah-de-blah. Anyway, let's keep dividing by 2 until we get to a number which can't. So we divide 256 by 2 and we get 128. We divide 128 by 2 and we get 64. We divide 64 by 2 and we get 32. We divide 32 by 2 and we get 16. We divide 16 by 2 and we get 8. We divide 8 by 2 and we get 4. We divide 4 by 2 and we get 2. We divide 2 by
unexpected item in bagging area.
2 and we get 1. We divide 1 by...
I got the little shoes dirty, goddamn!
Oh wait, that's an odd number. Gotta stop there. That means, if you were keeping track at home, we've divided 516 by 2 9 times. What that is also equivalent to is 2 to the power of 9. Now, there's something special about that 9. I can't quite tell. I'll just take a look at this grid and think where that 9 could come from. Just a little look. Where could that 9 come from? You see it? Oh, you're a special little boy or gal if you've seen it. That is right. It's 3 times 3. So, now we can expand this into the general case. That's the interesting part. So, what we've got now is that given any square nonogram puzzle, we know that the amount of state space searches must be 2 to the power of the width of the nonogram puzzle to the power of 2. We can test this by plugging 4 into where the n is, giving us 2 to the power of 4 to the power of 2, which is 2 to the power of 16, which is the number we said before.
Damn, boy! He's thick! Boy! That's a thick-ass boy!
We can even take this generalization a step further and have a look at nonograms which aren't of equal width and length. I'll put a 4x3 nonogram grid on the screen now. So to get the state space for this nonogram, we just take the width, which is 3, and the length, which is 4, times them together to get 12, and then do 2 to the power of 12. And that gives us an answer of 4096. The older method, which was the manual way of going through the state spaces, also applies for these. Just do the same thing. One fun math fact for you is that all of these odd-shaped nonograms are going to have the even rule applied to them. What do I mean by the even rule? Well, there's one state when you're exploring all of them manually which you don't double. There will always be that point when you have an odd width and an even length, or vice versa. We could further solidify this conclusion by doing a bunch of other mathematical things. However, if you just Google it, the answer will be there. So that's pretty solid most of the time. A lot of the people lie on the internet. However, in terms of mathematics, it's hard to find that, because you can't lie about, well, you can lie about numbers, whatever, fucking even though you've already seen the amount of state spaces you can have in a 10x10 nonogram, I thought I'd just show you how fast this thing just goes once you go up from 3. So the next one is 2 to the power of 5 to the power of 2. That number is 33,554,432. Then after that comes 2 to the power of 6 to the power of 2, a 6x6 nonogram. That is 68,719,476,736. The next level up, 7x7, broke Google's calculator, and by that I mean it doesn't show all the full detail. So I went to Wolfram Alpha. The next number up is 562,949,953,421,312.
Wow.
So the next one up, 8x8, managed to break Wolfram's naming algorithm. So I had to fix that. Anyway, that number is 1,044,474,709,551,616. And finally,
wow.
9x9 nonogram. This one, I'm having to rehearse these numbers because I don't want to make a mistake. Anyway, 9x9 nonogram is 2 septillion, 417 sextillion, 851 quintillion, 639 quadrillion, 229 trillion, 258 billion, 349,412,352.
Wow.
I thought a fun thing we could try is have a look at it on the graph. So here's the graph of 2 to the power of x to the power of 2. As you can see, it's quite similar to the graph of x to the power of 2. However, except we never touch the x-axis, and that's because we can never get this term below 1. Think about how powers work. And I just wanted to show you how long it would take to go from the coordinate 2, 16 to the next one up, which we know as 3 and 512. So let's begin. Again, I'm going to put music here. Feel free to skip to the end. I'll put a timestamp here, please, in editing. Come on. Okay, music.
If you're a fucking fair dinkum fucking full-grown Aussie, this is what you'd have for breakfast, you fucking dog cunts. A fucking VB Longneck at 20 to 8 in the fucking morning. Get that up, yeah. Get that up. Get that up. Get that up. Get that up.
And there you have it. 3 and 512. Well, that was a little bit underwhelming. Anyway, there's one last question I wanted to ask. I finished that nonogram running in the background. It was 40 by 40, and it's this little doll. Whoopsie-doo. However, we don't know the state space search for a 40 by 40 nonogram. Well, we know how to calculate, so the answer is 4444624177094. 044. Well, thanks for watching. This has been my first big edit attempt at a video, and quite frankly, it was fun to make this, and quite gratifying as well. It was very nice to explore the mathematical concepts that came up. This all started off with a Python coding project. Me then thinking, oh, I could test some editing chops, which is something I said in the start of this video. Well, I believe I did. I can't remember what the edit is now. Anyway, but yeah, just something I could test editing with. I had a couple of videos I wanted to try making, but I have to just see where the wind takes me, really, because I've got loads of little things going on that I really enjoy doing. I'm not really restricted to this video editing platform. I've got loads of other projects I like. I've got that coronavirus spreadsheet, which you can see on my channel. I've got a video game jam that I wanted to participate in. I have things coming up in the real world, which I'm not going to talk about here. And just loads of things that I have to try and keep a balance and afloat. But yeah, I hope you also learned something from this video. I tried to make it as educational as possible. I don't know how well it's going to come across to an audience which might not know me that well or don't quite get the cut of my jib, but it's just, I just felt like being natural, and I mix education with just weird shit, and it works. Also, this music is very calming, very nice. Ooh, a swooby-dooby. Yeah. I feel like there was something else I wanted to say. What else did I want to say? Oh yeah, you could also probably hear in the background me saying every single digit for the 2 to the power of 40 to the power of 2 nonogram. This number is massive. I did say every number. I had to double check that I said it all right, so that took me a while. But fun mathematical facts, I'm going to go back to the maths. This number is bigger than 54 factorial, which is the famous amount of ways you can sort a playing card deck. There's also many visualizers out there already showing how big that number is, so just imagine a number bigger than that. Ooh, scary. Anyway, I just want to clarify some mathematical bases before I end. With all the stuff where we're going through all the, what are they called, configurations. You can't have overlapping lit up squares, of course. We treat each lit up square as identical, so there's no unique difference between them. And you cannot count the same configuration twice. I think those are good bases. So yeah, if you think I've missed anything in mathematics, please tell me. I would actually much appreciate that, because I feel like I've got everything but you. You never know, you're never perfect. Anyway, this has been Picachuat saying bye bye. 364-645-376. Oh, Jesus Christ.